Welcome to the next lecture of Software Design and Modelling. What we're going to do today is we're going to look at the UML big picture. So we're going to wrap up what you know about UML so far, and we're going to talk a bit about UML as language. So this is roughly what we're going to do. I don't think I'll read these out. So remember, I said earlier on that in the 1980s and early 90s there was an explosion of object orientation, which was perceived as being the silver bullet that was going to solve the software crisis. There was a plethora of gurus, each with their own tool and company and book and modelling notation. And among these people were Booch, Rumbauer and Jakobson, the three amigos who originated UML, the Unified Modelling Language. But there were also a whole bunch of other people like Code, Odell, Schleiermacher, Sprock, and so on. So to say a bit more about it, one of the most interesting documents to look at is, and you can find this online I think, is this 1993 issue of the Journal of Object-Oriented Programming, in which there is both a guest editorial by Ivar Jakobson entitled Time for a Ceasefire in the Methods War, so he's talking about the need for standardization, and an open letter to the industry entitled Premature Method Standardization Considered Harmful, signed by a bunch of 8 methodologists but not by Jakobson. So that's very interesting to look at, and it's documentary evidence of what I was saying earlier on, which is to say that there was pushback from the community about the idea of standardizing methods as opposed to notations, which is why we ended up with what is arguably the first instance of a modelling notation which is deliberately detached from the associated method so that it can be used with different methods by different people. So how this was resolved was that Rumbauer joined Booch at Booch's company Rational, which by the way is part of IBM now. They claimed that they were going to standardize, that they were going to produce this unified method, and Jakobson joined them at Rational. Then we had all 3 amigos. But what ended up being produced was not a unified method, but a unified modelling language. And so we ended up with UML itself in 1997, and then various different versions of UML going forward. And then as a kind of separate process, we also ended up with the Rational Unified Process, which is kind of the method side of that, which is which has not become standard in the same way as UML, the notation. And there have been persistent issues around what it should really mean to standardize a notation, driven by the difference in methods and the difference in the ways that people wanted to use UML, because depending on exactly how you want to use the notation, you'll probably have a different idea about exactly what certain diagram elements should mean, and in particular about how formally they should be treated. So splitting the method from the notation is not completely a free lunch. So parts of UML that you already know about, the use case diagram, which summarizes the requirements. Remember always that the use case diagram is not itself the thing that gives you the detail about the requirements. You can think about a use case diagram as being, if you like, a contents table for a requirements document, which is more properly considered as the collection of the use case texts. So for each use case ellipse on your use case diagram, there should be a bunch of standardized text behind it that says, what does this particular ellipse really mean? What are the steps that the system and the actors have to go through in order to carry out this coherent chunk of functionality? You know, of course, about class diagrams, which show the static structure of the system. You know how to use sequence diagrams, which record how objects interact, which is to say inter-object behavior. And you know how to use state diagrams, which focus on an individual class and show how objects of that class undergo state changes when they receive messages. So that's intra-object behavior. So those 2 things are complementary there. And you've also seen activity diagrams, which get used principally actually at a business level to record workflow, although sometimes people like to use them in other ways as well. There's a whole bunch of other stuff in UML. UML is a very large language and nobody ever uses all of it, and in particular we don't teach all of it in this course. There are actually 3 other kinds of interaction diagrams. I decided that sequence diagrams were enough to teach, they're the most useful. There are deployment diagrams which show how processes in the eventual system are deployed to hardware. These perhaps aren't quite so popular. They tend to either be too simplistic or unnecessary depending on the setting, but they're there if you ever want to use them. And package diagrams show how the overall system and its namespace is organised, and actually we'll see some examples of those later in the course. You've also seen object constraint language, which is a textual language for describing constraints. Recall that a constraint is simply an expression that might be true or false in a context. And later on we'll talk about design by contract, for example, which gives you one setting in which you'll very much want to use such constraints. Although you might already use them in the context of a conceptual class diagram where you wanted to describe that certain configurations of objects are to be expected and others are not. And there are also a whole bunch of facilities for defining profiles, which is to say variants of UML for particular domains, and we may mention those briefly later in the context of domain-specific languages. We'll see. You don't need to use all the notation, so no project uses all of UML, and indeed many users only ever use a small subset of it, so quite a lot of people just use class diagrams and sequence diagrams. And it really depends on the needs of the project. Embedded system development quite often uses state diagrams extensively, especially if they're using tools that mean that the code can be generated directly from the state diagram, so that developing a state diagram is programming, if you like. Business software development seldom needs them. And there are several recent papers that have looked at what parts of UML are used, how much. It's a difficult area to research convincingly because you tend to have to use a convenience sample, but I may put some of those in the required reading. And we'll come back at the end of the course to talk about how the available tools influence the way in which models are used and how that might change in the future. So a source of confusion and bugs in software development is when you have different diagrams and documents that contradict one another, of course. Well, how can that even be? What do we mean by this? We say that a set of diagrams is consistent if there is at least one way to implement a system that they all describe. I think this is the simplest and best way to think about this. So for example, all the classes and operations that are mentioned in a sequence diagram had better also occur in the class diagram. So for example, if you're developing a sequence diagram, perhaps in response to a piece of robustness analysis or CRC card playing that you've done, and you add an object of a new class that you hadn't previously known existed in your sequence diagram, you haven't finished until you've also added that class into your class diagram, so that the two things are consistent and so on. And this is actually embedded into the definition of the modelling language. An inconsistent set of diagrams will not constitute a legal model, just as a Java program that doesn't compile isn't really a Java program. And just as in that case, the way people talk about it tends to be a bit confusing sometimes, so you actually informally will quite often talk about a Java program that contains an error without being pedantic enough to say that it isn't a Java program. And one of the ways this shows up in the modelling world is that sometimes you'll hear people describe individual diagrams as models and talk about consistency of different models, and sometimes you'll hear people talk about the whole collection of diagrams as being a model, which only really exists if the diagrams are consistent. And it doesn't matter very much, it's just sometimes you can trip up over it a bit. So in what sense is the unified modelling language a language? Well, let's think from a very high level what actually a language is. So you can think about a language as being a set of possible utterances, things you can say in the language. And we fundamentally have 3 questions about it. We want to be able to say, is an utterance actually part of the language? And if we're talking about English, we might mean, is it grammatical? Okay. is it possible to say this? So you can say, coloured green ideas sleep furiously is a syntactically correct sentence. And similarly, you can write yourself a syntactically correct UML diagram. The more exacting level is to ask, what is the semantics of an utterance? If you have an utterance which is legal, what, if anything, does it actually mean? Okay, can you assign semantics to it? So in the case of English, this means, what does somebody understand from your sentence? In the case of UML, it's going to be, what does it say about the system that is going to be developed? Do we understand that? Does it actually correspond to a system that could be implemented? And then there's also a third level which sometimes gets missed out, which is the pragmatics, which is to say, what conventions do people use in using this language? So if you have several legal utterances, perhaps even meaning the same thing with the same semantics, which often seem most natural, for example. So let's look at these in turn. So UML syntax, this is the rules of diagrams. So you've been learning a lot about UML syntax. You've been learning which diagrams are legal and which ones are not. And UML's syntax is defined in the UML standard using metamodelling. And that's kind of largely automatable. The checking the syntax is largely automatable. Tools can, and to some extent do, check that your UML diagram really is legal UML. So some of the rules are complicated and many of them are not checked in any tool. Okay, but you've seen a bit about defining the syntax of modelling languages in the paleo example that we did earlier on. What about UML semantics? Well, again, I think this is the easiest and most practical way to think about the UML semantics. If you think about a diagram as being a statement about a system, okay, so the job of UML semantics is to explain what a diagram says about a system. Okay, so it might be that we say, well, what does a class diagram do? Well, if there is a class called customer in the class diagram, then what that says is that the system must contain a class called customer. Okay, and if I give you a UML class diagram that has a rectangle that says customer in it, and I give you an implemented system in Java that contains a bunch of classes but none of them is called customer, then what you're going to say is, okay, that Java system is not within the semantics of that UML class diagram. Okay, the system and the diagram are not consistent. Typically, because the diagram only says a limited number of things about the system, infinitely many software systems could be described by a given diagram. So, for example, the class diagram tells us what classes there are and what operations they offer and a few other things about how they're related and so on. It doesn't say anything at all about what those operations do. And so I could offer you an implementation in which those operations do anything at all, and that makes no difference to whether or not the system is consistent with the class diagram. Okay, so that's fine. The semantics of UML is defined in the UML standard using English. There's a huge amount of work on formal semantics, which is largely motivated by the desire to provide better tools, so to provide tools that can formally check, for example, whether a given implemented system correctly implements a given UML model, or perhaps even to generate one. But within the formal UML standard, the semantics is defined using English, and it has all the usual problems of trying to define a formal artifact like a diagram in English, which is to say that there are ambiguities and inconsistencies and problems, and sometimes you'll trip over some of those. You might, for example, find that different code generators for generating code from UML do different things because the people who wrote the code generators interpreted the same sentence in the UML standard differently. Then pragmatics tells us things about how UML is typically used. So I've talked quite a lot about what people usually do. A classic example is layout. So layout of class diagrams has no meaning in UML. It makes no difference where you position the classes in your class diagram on your screen. But of course that doesn't mean that the users of the diagram are equally happy with any arrangement. People typically arrange their diagrams with the most important classes in the middle. They try to have as few crossing lines as they can manage. You'll typically find that generalization arrows go up rather than down. You'll usually find that association names are designed to be read from left to right, even though UML class diagram notation provides this little filled-in triangle notation that lets you say, no, read the association name from right to left. It's just less natural for people. And this actually turns out to be quite important. So language designers may feel as though they can ignore pragmatics, but actually the fact that humans find pragmatics important means it's not so easy. So for example, if in practice you want to be able to move your diagrams between different tools, it turns out to be important to record the diagram layout, because people who have put effort into building a large model are going to be very unhappy indeed if it gets completely relaid out when they import it into a new tool. And this actually historically gave UML some problems, because in the early days there wasn't a standard way to record layout, and this had to be invented much later. And then for a time things were inconsistent between different tools, and that gave us other problems. Okay, let's go into a bit more detail. How do we define the syntax of a graphical language? We have to give abstract syntax and we have to give concrete syntax. And again, the distinction between these two in the context of a graphical language almost began with UML itself, although now this is quite well understood and quite mainstream. Okay. So the abstract syntax of the language tells us what the parts are, so what kinds of model element are there. So a UML class diagram, for example, may include classes, associations, generalizations, and how these different kinds of model elements can be related. So you might say, well, how does it make sense to use a generalization within a class diagram? Well, given a generalization, there should be some class which is the supertype and some class which is the subtype. Okay. And you also may want to say something about what the restrictions are. You may well want to say no class can be connected to itself by a chain of generalizations. Well, why? Because that's inconsistent with your intended meaning of generalization. And you'll have a choice about how much of the restrictions you actually document. Separately, you also want to record concrete syntax. You want to say, how is this all represented graphically? So in UML we say that a class is represented by a rectangle, we say a generalization is represented by a triangle-headed line, and so on. Now in UML there's a standard concrete syntax to go with the standard abstract syntax, but in recent years we've been realizing that it's often useful to have textual syntax for graphical languages, and also that once we've properly separated out these ideas of abstract syntax and concrete syntax, there's no reason why you shouldn't have several different concrete syntaxes for the same language with the same abstract syntax, which perhaps are more convenient in different settings. So that's quite a nice thing to be able to do, and we'll probably talk about this later when we talk about domain-specific languages. Notice, and this is why we talk about metamodelling, that defining the abstract syntax of a modelling language is actually very similar to describing the objects and their relations in an object-oriented system. So the question, or the statement, this model is correct in the modelling language, is really very similar to, very closely related to, and analogous to the statement, this collection of interlinked objects is described by this class diagram. We're just making objects in a running system correspond to instance elements in a modelling language expression, and abstract syntax concepts in the modelling language correspond to classes. And when you start thinking about, well, how are you going to develop a tool for allowing people to manipulate diagrams in my modelling language, these things might get very blurred indeed. You might end up saying, okay, my IDE is going to contain a class called generalization, and instances of that class generalization are going to correspond to, you know, the actual generalization arrows that the user decides to put in their diagram in my IDE. And then the instance of that abstract syntax concept in the model is going to correspond quite closely, perhaps, to an actual object in the running system, which is the IDE. Okay? So we really do have sort of different meta levels doing the same thing, and very similar considerations arise at the different levels. And what this means is we can conveniently describe UML's abstract syntax in UML, although we don't really need the whole of UML. So for example, even if we're describing the abstract syntax of, say, UML sequence diagrams, we're not going to do that in sequence diagrams, are we? We're going to be doing that in something that looks a bit more like a UML class diagram, because what we're going to be saying is, well, a sequence diagram has to contain some lifelines, some messages, and so on and so forth. Okay, and so we're going to be wanting to say what are the classes, we sometimes say the meta classes, that describe the elements of the sequence diagrams. Okay. Better, we can say that we describe the abstract syntax of a modelling language in UML, or a small subset of UML, or actually we can say we do it in a language which is specifically designed to be rather like a small subset of UML, which is the meta object facility. And I'm going to brush a whole lot of stuff under the carpet here. But what I want you to know is the meta object facility was standardised by OMG in order to help with the definition of the abstract syntax of UML, and it's since then been used for the definition of other modelling languages as well. You can think of it as a small subset of UML class diagram notation, and you should know that it includes classes, attributes, associations and generalizations. I would never ask you questions about precisely what else it includes or doesn't include. It's sufficient to express the meta model of a real modelling language, like UML, and it's simple enough to be shared by a whole bunch of different modelling languages, and, importantly, to form the basis of technology for things like model repositories and model transformations, and so on. So I'm simplifying the story quite a lot. You'll see a bit more about it later on when we talk about domain-specific modelling languages, and in particular I do expect you later on to know about the OMG 4-level metamodel hierarchy, but I decided not to put it in this particular lecture. So why is metamodelling a good way to design modelling languages? Well, it's reasonably understandable, especially, by the way, to the kinds of people who are going to be using modelling languages. And yet it's reasonably precise, and it lets you define abstract syntax. It helps you to structure your tools, and it makes it possible to define other modelling languages using the same metamodelling language, and that supports our use of domain-specific modelling languages and so on in a reasonable way. If we had to define a whole new set of language definition mechanisms and a whole new set of tools every time we wanted a new domain-specific modelling language, domain-specific modelling languages couldn't exist. So metamodelling supports that whole kind of ecosystem of things we can do. Don't worry if that doesn't make too much sense at the moment. That's all I want to say right now.